like the final exam days because then I get to see everybody. Sometimes I see people, I'm like, are you in my class? So, there's one thing I want to cover real quick that we did last time, and it's really neat, and it's an example of something, I've been teaching for a long time, and if you just don't have something come up, you sort of forget about it, but I was a little angry at myself about it, but there was a question about if I have something with the repeated bottom, why do we put A and B? Why don't we put bx plus c on top of that one, right? You with me? And it's a good question because, again, we have to remember the top is supposed to be 1 degree less than the bottom, roughly. It's just kind of a way to remember. But it's not perfect because this is second degree, it is. But the right way to look at it is it's a repeated linear, which means the top should be a single letter, a single constant, right? But it's a really good question. Why? Why the shit, Jeff? So very quickly. Everybody cool with this, right? Can you reduce either one of these at all? Can you reduce them? No, hell no. Okay, so that is it. Bedrock. So let me show you something kind of nifty. If I take this, isn't this the same thing as 5 over x plus 2 plus 1 over x plus 2? Isn't that the same thing? Yeah. Right? Would you ever do that? Probably not. Very few reasons why we'd do that. It's perfectly fine the way it is. But I'm a weird person, so I'm just going to do it. Can you combine those? Take a minute and combine those. Right, you better not tell me 3 over something. Unless it really is 3 over something. And it ain't 3 over So it's pretty simple, right? You have to multiply this with my x plus 2, top and bottom, correct? X plus 2 plus 2 is x plus 4 over x plus 2 squared. So there is an a and a bx and a c, correct? But is this the only way I could break this up? How else could I break it up? Somebody else give me another way I could break 6 up. Holy shit. So 4 plus 2. These are all equivalent statements, correct? This is equivalent to that. This is equivalent to that. What do I get when I combine these two now? I get 2x plus 4 plus 2 is 2x plus 6. Another A, another B, another C. Yes? Are you at this? You guys with me? Are you with me? I mean, that's equivalent to this. That's equivalent to this. It's like doing this. 7 over 4 plus 5 over 4. That's equivalent to 8 over 4 plus 4 over. Right. I just took one of those and put it over there. Of course, they're equivalent, correct? Whoop-de-doo, right? So if I use this, I am not going to get an answer because there's an infinite number of things these could be. How many ways can I keep going? Is this the only other way to break that up? No. What's another way to break it up? Holy shit. What about 8 and negative 2? What about 1.5 and 4.5? Does that work? Yeah. Shit. So there's an infinite number of ways. If I say it like this, I am never going to get an answer. But what is every single way? Every single way is this, aren't they? They're all that. Every single way I can imagine is this. So of course I do this, because then there's only one possible answer for what A equals and what B is. Yes? Okay, cool. I mean, it's an example of a really good question about why isn't something some way. And the normal way I explain it is, if you did, so normally I'll start here and I say, well, you can combine them. But it's still kind of like lacking. It's like, well, so what? I did get an A and a B and a C, Jeff, because there's an infinite number of A, B's, and C's. So that answer could never be gotten because there's an infinite number of things it could be. Okay.
If you're starting with a problem and you have like x plus 1 squared in the denominator, I know how to put like a plus b where you go a over x plus 1 plus b over x plus 1 squared. But why do you do that?
That's what this is all about.
The denominator is the same thing?
Well, it's a over x plus 1 plus b over x plus 1 squared. That's what it is. Yeah.
Yeah, just like splitting up the denominator into, like if you just start with one term and then put it in two terms?
Yes.
Okay.
Okay. I like it. And again, it's kind of because, can somebody give me a problem? Give me a problem, so it's a single fraction that would look like that. That would be the first step of partial fractions. Can somebody create a problem? What would be on the bottom?
X plus 1 squared.
Yes. Give me an example of something that could be on the top, like a specific something. I love you guys. You're all like, I don't know, man, what the shit. So I'll help us out. Okay, there. Right? You with me? So why, now, even on this level, do you see how this doesn't make a freaking shit worth of sense? Isn't it already something x plus something? So would a just be 0 and then, you didn't do anything then? Good job, yay. So the idea is, where could something like this come from? Well, it could come from something over x plus 1 plus something over x plus 1 squared, because then I have to multiply this by x plus 1. I get an x piece and a number piece. Do you guys see that? Yeah. Then the question is, why is it a and b? And that's what all the stuff I just did. That's why it has to be a and b, because if you let it be bx plus c, there's an infinite number of ways to do that. How can you ever get a specific answer when there's an infinite number of ways to do something? I want to have it so there's only one. So if I put a and b, there's only one way to get that to work. Okay, maybe. Sort of like, here, you guys, let's go way back in time. How do you solve this? Set each piece equal to 0. Okay, how do I, right?
Yeah.
So it's 1 and negative 4. How do I solve this? Do I set each piece equal to 8? No. Shit, no, why not? Because if each number was 8, 8 times 8 would be 64. More generally, how many numbers multiply to be 8? Huh? So what'd you say?
I said a couple.
A little more. How many numbers multiply 8? Yeah, why? Give me 2 numbers that multiply 8.
2 and 4.
Neato. 2 more.
8 and 1.
2 more. -2, -4. 2 more.
16 and 4, 5.
There it is. 16 and 1/2. What about 800 and 1 over 100? Yes? Isn't 800 times 1 over 100? So infinite number of frickin' ways. So I'd much rather have it set up so it's equal to 0, because then I know one of these must be 0. That's effectively what this is doing. There's only one way for this. If I do this, math ain't never going to work, because there's an infinite number of things it could be. Okay, if you just came in on the tail end of that, I'm sorry. Too bad. Watch that on the video. Okay. So the shortcut way, just to remember, is a power on the outside is just repeats. This is the actual degree. That's why it's a first degree. The top is 1 degree less, constant. Okay. And the repeats have to show up that many times. If it was a third power, I would just have a third c over x plus 1 cubed. Okay. Don't freak out. The partial fractions problem I give you in the test is not going to be near as long as the one I gave here. I just wanted this to be a good general practice. So I had a couple of things in there. Okay. All right. So your homework from last time was to come ready with questions. And apparently, over half the class could not find questions, so they're not here. So, hey, which is fine. Hey, I'm not gonna, you guys are gonna get A's on that final. Shit, stay home. All right, Jeff. A little passive aggressive. Yeah, I'm afraid so. But yeah, anything you guys want to talk about? Anything from the whole semester that hasn't made much sense or whatever you need to see another example of? You just have general questions, right? no question is too crazy. Well, we'll see. Go ahead and test me on that. Yes.
On the fourth test, it seemed like a lot of people got the more resolution comment.
Yes.
I'm assuming there'll be something like that on the final, but how would we know to use more resolution?
You almost never stop at just the whole numbers, especially when, I mean, that one was composed of a quadratic and a trig. So it could do very unexpected things, right? They are generally nice functions, but we don't every day work with combinations of quadratic and trig. So you really should give yourself more, because I want to see a little more detail in the thing. If the answer really is this, and the answer you give me is this, no. Does that make sense?
Yeah.
Yeah, okay.
So would you recommend intervals of half, quarter?
Yeah, if I give you, now if I give you like a range for t from 0 to 1, you might want to break it down to at least a quarter of a step, right? Maybe even a tenth.
Okay.
Yeah. You just generally want more resolution for these unknown shapes.
Okay.
We have worked with parametric stuff so little that we should need more data to help us get it sketched. Yeah.
Okay.
And you know, one of the two was, more like this, but the other one was more like this, so, yeah, so you just don't want to make too many assumptions with something you're not familiar with. So you want to be a little more, that's why I liked it when some people were using, I didn't take any points off, I didn't say anything on the back on number 6, but they're there. So why not go ahead and use pi over 12, right? You can do pi over 12 steps. Because like I said, most of those, you're not going to have to put pi over 12 for the whole damn unit circle. Holy shit, you only have to do a few and then you can kind of see where it's going. Yeah. But why not use it? It's there, right? It'll help you get that curve better, right? Okay. Okay, so more resolution in general. Crank the resolution up to 11.
Can you do a 6B from test 3?
Oh, so here we go. So I don't know, which one did you have? The cosine squared of x or the sine of x squared?
Cosine squared of x.
Okay. So, can you make your question more specific, or like which piece of it? So I'm assuming you got 6a correct.
Yeah.
Okay.
It's just the integration of that part, using that part.
So I mean, just to be fair, I'm gonna make a different one. Not too different from this, but a little bit different. Yeah. All right. So say I had this. Let's make this over. Sure. And I want to integrate this. Right? So the only part of that entire series that the integral cares about is which one? All the rest of it is a constant, so it only cares about this. So basically, you just write everything else. Everything else just kind of comes for the ride, just like a number would, right? So what's the integral of this?
X to the 2n plus 2, all over 2n plus.
Yeah. And then if it's from 0 to 1 or something, then you want to write a few elements out. Like when n is 0, I would get x squared over 0 factorial, 4 to the 0 is 1 times 2, right? Plus, and then I'd write a few more terms out, and then I just plug a 1 in. Because the 0 would make everything 0, of course, which is nice, right? Okay. And I just have to make sure I go far enough here so that I get it. Yeah, so I start here, and then I add the next one, and I see how much it changes, add the next one, see how much it changes, and I keep going until, if I want the first three, I keep going until the first three don't change. Then I know I'm good, because they keep decreasing in size. Okay, maybe, is that cool?
Yeah, that's a lot.
Okay. So I understand, when you see this kind of, I mean, my God, imagine me showing this to a Calc 1 student right after they learn integration. Their heads would explode, yes? But we know all this shit, this just means a bunch of sums. Just a sum of a bunch of terms, correct? And I can just integrate each term in an integral. I can just integrate each piece. So that doesn't do anything to me. These are constants, right? For a given value of n, these are constants. So all the integral cares about is the x stuff. Everything else just comes for the right. So like, how do you integrate 5x?
5x squared.
Yeah, the 5 comes to the right, and then x squared over 2. So you might not have ever thought of it that way, but the 5 just comes for the ride, the x is x squared over 2, right? Okay, so that's why we don't give a shit about constants. They sort of come along, yeah. Okay, maybe. No, we care about them, you know. Just a little bit. Okay. All right, okay. So we did number 5 last time on the answer key. I was very lazy. I just said did in class. So if you weren't here, it's on the video. 6B, I think I said last time, is going to be, if it's on the final, it's going to be a bonus question, but it's
Do you mind doing one of those problems? Where you find the area under?
yeah, it's so let's see. I don't know. Well, let's make one that's not too freaky. So if x was 1 minus t squared and y was t cubed plus t. If I start with, and let's say I want from 1 to 2, sure, right? So if I start with this, what is y?
T cubed plus t.
Good. What is dx? Keep going, yeah, right? I really want you to understand. Y dx. And now my variable of interest in its integral is t, and what is t doing? Going from 1 to 2. This would be what x is doing. I don't know what x is doing. I don't give a shit. This form just helped me set up this, because I know what y is. I know what dx is. And then t is my variable interest. These are now, what the book has is alpha and beta. Those are just what t is doing. And then that's, I'm not even going to do it. It's just polynomial. Who cares? Multiply that out, integrate that, plug the 2 and the 1 in there. Right? Okay.
What number is this?
6b, and again, that's pretty simple. So it's you should be able to do that bonus problem, but it will be a bonus problem since we didn't officially do section 10.4. It's actually pretty simple. It's the yeah. Wait, did we do this? Let me think. We didn't do the polar calculus stuff, right? It was the polar we didn't do. This we definitely did do. Yeah, I'm getting those two confused. I'm sorry. It was the polar calculus stuff we didn't do, like the number 1 on the last test. Yeah, so this could be on the test. This could definitely be on the final, easy. And again, I would say the same thing I said there. My hint would be start with this. And all you do is replace what you know. I'll tell you what t is doing. And then you just go.
And then the polar coordinate one was the.
Would be the extra credit one, because that's the calculus, 10-4 was calculus for polar stuff.
And
We
that's-
did 10-2, which is the calculus for parametric.
Right. But that would generally be the 1/2 r squared.
Yeah, exactly, 1/2 r squared d theta, integral of that.
Okay.
So that would be a bonus question if it's on there, yeah. Yeah, okay. I think I told you guys, I don't know, I'm not really sure. I haven't made the final yet, so I felt like the practice final was a little series heavy, but looking at it now, I don't know. We'll see. Yeah. Maybe it's got one too many problems on it. Yeah. If you weren't here earlier, number 3 on the practice final, I just kind of constructed it to be a nifty power series, and then I realized the endpoints are not doable as far as much calculus as we know up to this point. You'd have to know a little bit more. It would be doable, but it would take some math induction. It would also take some creativity, because when you have the factorials in there, you can't do derivatives too easy. You guys don't know what the derivative of factorial is. If you think about it, do you think it's simple? If I have a factorial, I have to only take a derivative of it. Do you think that's easy? Shit, no. Yeah. So. So again, I am wide open. As normal, I really didn't bring much except for that thing we did at the beginning of the class. I didn't really bring anything else. So
just for our test before.
really dependent on what you guys want to focus on.
Oh, yeah. I have a question on it.
What's up?
2C. The practice.
On the practice file? This one?
Yeah.
Okay, yeah. So it's got, you can pick it up, Jeff. There you go, buddy. Did anyone try to do a ratio test for this? Oh my God, I would not want to do ratio. Okay. Ratio test would be heinous. What's the one test we use the least frequently? Yes. Root test. So what is going to just scream at you? It's going to be really obvious when it's root test's turn. Right? It's sitting at the end of the bench. We're like, root test. And he's like, huh? Get in there. Oh, thanks, coach. So what is it about this that's telling me the root test is going to be good?
They're all to the power of
Yeah, they all have a power of n, right? Now this one, of course, is 2n, but that just means this squared to the n. So now, try you, root test. Good. I'll wait. Let's see, I got up to double digit attendance, okay. Small victories. All right, poor little dude. So you can rewrite this as n plus 1 squared to the n. So now it's just all the. So then I get 4n plus 1 squared over 5n squared plus 3. Then, all my markers. And then that, see if any of you, oh, look at you. What does that equal to?
4/5.
4/5, yeah. Same degree, top and bottom, ratio of the highest coefficients, the highest degree coefficients. And that is, how do I interpret that? Less than 1, which means this converges how?
Absolutely.
Sweet. It absolutely converges. Its abs converge. That's all I got, man. That's all I got. Silly freaking jokes. That's all I got. Okay. That's pretty nice, right? I mean, the ones where root test works almost have to be simple. I mean, the minute the nth power gets out of the way. The only way, well, I mean, there's a few ways I can make it worse, but I don't think I will. So, yeah, you just have to notice. I almost want to make you do this. That's why I asked, did anybody try this problem, try ratio test, or did you guys just sort of like, oh, see what happens when I get there? Anybody? Real quick, just for shits and giggles, let's try to see what would this thing look like if I try to do ratio test. Tell me out. What would it look like?
4n plus 1. And n plus 2.
Yeah, that's where things get shitty.
2n plus 2.
Yeah.
Yeah.
And then here,
5n plus 1 squared.
yeah. To the.
N plus 1.
Now, do you start to understand how the bases to the nth power are not going to be equal?
Yeah.
All right. I shouldn't have to go any further.
Yeah, it's terrible.
That's where the E stuff comes from, correct? God, ain't no way I want to do that shit. So if you start to get to a point where I really want it to make sense because, so here I got 5n squared plus 3 to the n over 4 to the n, n plus 1 to the 2. So I mean, these are the ones that are working nice. Look at that. They got the same base. Do these have the same base?
No.
Oh shit, I can't just kill so many of them because I don't have the same base. I don't have the same amount of anything. They're totally different bases. Same thing here. Yeah. So you'd have to do something a lot more complicated with that limit. You might have to do logarithmic limits and such. No. So if you start to notice stuff like this, where the bases aren't even the same, back up. Maybe it's a root test, right? So basically, since root tests happen so infrequently, it's not a bad idea just to rule it out real quick. You know I'm going to give you a problem when there's root test. You know I am. So for each one I go, root? No. Okay. Root? No. Okay. Just because you don't want to do this to yourself, and then you start doing weird shit, and I don't blame you, because it's weird. So don't do that. Okay. Yeah, I like it. By the way, real quick, there's one thing I never showed you guys that it's just gonna explain one little thing, but it just came to mind, so I want to do it real quick. This is on the answer key, so I can just erase it. Remember when you do the ratio test and the limit's 1, what does that mean? Inconclusive, I love it. So what if I had this versus this? What's true about those? This one converges, this one diverges. So let's try to test this using the ratio test. Let's use a ratio test, right? Is that cool? Because it'll be 1 over n plus 1 squared divided by 1 over n squared, blah, blah, blah. Right? Well, what is this limit? Immediately. 1. All right, let's try the ratio test on this. Right? Again, what's the limit? The limit of any polynomial ratio with effectively itself. Even if I put a 2 here, won't this be a 2 and this will be a 2? So the limit's still 1, correct? So the limit of any polynomial in a ratio with itself effectively will be 1. That's one example of why it has to be inconclusive. Because I got a 1 in both of these, that diverges, that converges. So it's like, could be one of those two things, we don't know. So that's why 1 is inconclusive, because it can't discriminate between those two situations. It's like, dude, I don't know. Is that better? I always forget to say that. I've told that to a few people I've been tutoring, and I'm like, I never did say that in here. Shit. Anyway. I don't know if anybody's really like worried about why limit of 1 was inconclusive. But yes? Which one? 1D? 1D, okay. Oh! So what kind of method do you need for 1D? Yeah. Are we at the point where you guys can just tell that's a by parts? I mean, yeah. The natural log of x really, the natural log of x is like a classic component of a by parts problem. Because the integral of natural log of x by itself requires by parts the first time you do it. Okay. How many times do you think you're going to have to use by parts? Well, okay, we have to go and see. Yeah, we'll see.
2.
Yeah, you're probably going to have to use it twice. If it was that, I would expect once. Yeah. Because, of course, what are you going to let u equal? Of course you're going to let equal natural log of x. So that would know shit the integral of that is. Actually, you probably do. But, so then what's dv got to be? 1 over x squared. All right. Yeah. And here's the idea. Remember, if I had something like integral x sine x, that would take 1 by parts. This would take 2 by parts. Yes? Because I would let u equal this. And have to do it a couple times if the derivatives kill it. Yes? Opposite idea here. If I integrate this once, it's now to a first power. So I have to integrate again to kill it. Yes? It's kind of backwards. It's kind of different. I think. Maybe I'm thinking wrong. Well, let's see. Actually, I think this might just take once. Let's see what happens, especially because this guy is going to give me a what? 1 over x. And this guy is going to give me, yeah, negative 1 over x. So when I do the integral of v du, yeah, we just need what? 11. That's the mistake of trying to think too much ahead, not just doing it. See what happens. Plus, you'll get the integral of 1 over x squared. Yeah, okay. So ignore everything I just said. I was making too many assumptions. What's funny is I just did this morning on the key, and then I forgot, oh yeah, you just need one time. This form, now of course you have to plug stuff in, so this is still being evaluated. Right? But I'm obviously not going to give you this exact problem, but very often by-parts problems sort of stick out. They have definitive pieces to them, right? If that wasn't there, that integral would be easy. That kind of, if that wasn't there, the integral would be easy. So if you catch yourself saying that or thinking that, it's very likely by parts. Okay. Now, you got to be careful because we have this problem. I think it's number 1. If you try to do that by parts, you will very quickly go insane. Now, that has an obvious component to it that tells you what it is, right? What's the obvious part to it? Yeah. It's got something that looks like it's related to a trig sub. If I substitute x for a trig function, yeah? Okay. like it. Remember what I said last time? If we turn this around, what would it be? Like, why is this not a u sub right now? Yeah.
Because the derivative of 2x
It's
minus
x, and I have a 1 over x, not an x. Yeah. So if I flipped it, u sub works. Yeah. And trig sub would work, but my God, why would you? You guys see that? So if I flip this around, now of course, I'm not saying you can't. That's, please, dear God, please nobody think I just said this is the same problem. If the problem would have been this, u sub. Because now the derivative of this is here. The derivative of x squared is 2x, which is not in here anywhere. I have a 1 over x, not an x. Yeah, okay. I'll lock it.
Problem similar to
1C.
trig integrals.
Yeah. So are you, like on 1C, does the fact that there's a 2x on the inside bother you that much? A little bit, okay. Okay, that's fine. I can deal with that. But it should definitely not bother you a ton. So what if I had this instead? Is that definite or indefinite? Yeah, okay. Oh shit. Now instead of just memorizing the stuff, what are the two possibilities for you for this kind of a problem? When I say you, I don't mean you, I mean you. What's the two possibilities for you? You could either be secant or tangent. So if you just sort of, if you say, okay, u equals tangent, you're not saying that's what it is, you're just going to go, let me go down that road a little bit and see what that would then mean, right? If u is tangent, what's du? Good, 4 secant squared, right? Good old chain rule, yes? I have secant squared, right?
Yeah. It's just the one before it,
Yeah. If you did, now what's funny is, so let's see. So then this would be u cubed, right? And this would be your du, yes? What if you tried secant? What would the derivative be?
Secant x tangent.
With the 4? And be careful when you say x, you really mean whatever's there.
Yeah.
Okay. Would that work? Totally. One of these secants is u. Then you have a secant tangent, and then you have a tangent squared you can replace with secant squared. Would you want to do it that way? Shit. So sometimes both ways work. One of them preferable. Do you guys all understand? Can you guys see that each of these would work? I have one secant that's for u. I have a secant tangent that's du. Right? I don't care about the 4. I can make the constants work. And then I have a tangent squared I can replace with secant squared minus 1, and that would be u squared minus 1. So that would work. But I ain't going to do this because that's a lot of shit. If I want to do that, what would it look like? So this is almost du. I just have to do it. Yeah. Very different color here. Look at that. Wow. So now that's du. And this, u cubed. That's silly, I know. Don't forget your 1/4. Okay. All right, and then blah, blah, blah. Easy. But yeah, just, it's fine to go, okay, what if I made you that? What would that mean? What if I made you the other thing? What would that mean? It's not even a question of is there something wrong with it. It's like, do that shit. That's what you do, right? Okay. And sometimes only one of them will work, and sometimes one of them will be better. Okay. if that problem is offensive. No, it's fine. Okay, is that cool? So every time we've discussed a new idea, I've desperately tried to get at the underlying concept, like why would this work? Not memorize this. That's insane, right? The people that think I can't do much math, how do you know so much math? I don't know as much math as I do. I don't. I know underlying things and then I play with them and I do more shit, right? I don't memorize every damn thing. There's no way I have that much room in my head. There's no way. I'm already having to forget stuff just to make a little more room. That's my excuse for not knowing everybody's name. I suck with names, but oh well. Poor people, I'm like the last day. What's your name again? Like, come on, man. It's just the way it is. Yes?
Could you do, 5A is a Taylor series or just an example of a Taylor series?
So we did 5A specifically last time. So just to say again, on the answer key, I just said 5A did in class. Because I didn't feel like doing it all again.
Or just like another example.
Yeah. Let's see. I don't know. Is there a function that you're curious what its Taylor series is that we haven't looked at? Or is that too weird of a question? Natural log. Okay. So I want to ask you this. If I do this, can I do a Maclaurin series?
No,
Why not?
because 0 is out of bounds for that.
It's undefined as 0, yeah. I love it. So we'd have to build it around something else. And what's a good A? If you had to pick an A, what would you pick?
1.
1, yeah, why not? Yeah?
Yeah.
Shit, yeah. Because, of course, then it's going to be nice. So the process is you just start making a bunch of derivatives, right? And what I try to do is to show you, you could start getting the numbers. And sometimes the pattern is easy to see with the numbers. But sometimes the pattern is easier to see before you plug stuff in. So I just was trying to show you how to do either one, right? So let's try to do this just looking at the numbers and see if we can get it. I'm not even sure, well, we'll see. So what's f? So f of x is ln x. What's f prime?
1 over x.
Let's see. Sweet. What's f double prime?
Negative 1 over x squared.
F triple prime.
Negative, 2 over x to the third.
F quadruple prime.
Negative 6 over x to the fourth.
Yeah, and you can start to see the pattern there, right? At least not starting here, of course, because that does not flow into anything. But starting here, maybe, right? Or even, what's the pattern on the tops? Let's start here.
Positive, negative, positive.
Well, sure, okay.
Oh,
There's
yeah.
alternating. Take that out.
Yeah.
What's the pattern? You guys know those numbers yet? Factorial. Yeah.
Okay.
So I could right now this is a little bit of a simple one, but I could right now, it would be -1. When n is 1, it's got to be positive, right? So I want the power in this to be
N plus 1.
n plus 1 and -1 either way. I'll do +1 because I'm trying to be positive. The tops, like you just told me,
Factorial.
yeah, and let's be careful. When n is 1, 1. When n is 2, 1.
Oh.
So this is what factorial?
N minus 1 factorial.
This is 0 factorial, 1 factorial. Yeah, so it's 1 less than the n, so it's n minus 1 factorial over x to the n. Yeah, that kicks ass. And that's true starting at n equals 1.
So when you can start seeing the pattern after the first, is that kind of like a sign that's going to be n plus 1? Because I always get myself mixed
When-
up on when
so-
you know.
If I thought it was n factorial and I check, so if I write
Oh
this,
no, I mean
Oh.
-1 to the power of n plus 1.
oh, that one's pretty straightforward. If it's supposed to be positive at 1, it can't just be n because -1 to the 1 is negative. Yeah. Okay. Now let's put some numbers in. What's f of a?
0.
0. What's f prime of a?
Negative 1.
Just 1.
Just one. I don't know. Got a little broken up. 1. F double prime of A. Negative 1. F triple prime of A.
2.
F 1. A.
-6.
Negative 6. And real quick, if you look here, it's a pretty simple pattern here, right? So I should have stuck with what I said. I was going to go to the numbers and see if we can see the pattern. If you get to the numbers and you can't see the pattern, very often because they're fractions that have been reduced, you might be able to see the pattern better here. Now, what is this pattern? And I want to show you why they're the same. What is this pattern?
Factorial.
Starting here, because we can ignore this guy because he's 0 anyway. Yeah, what's Fn evaluated at 1?
N minus 1 factorial.
N minus 1 factorial.
Times -1 to the.
Yeah, -1 to the n. And of course here, why are these the same? Because x is 1. So of course that equals that, right? So you can get the pattern either from the numbers, but very often the numbers are misleading because they reduce or something, right? Or you can get the pattern from here if you can't see it there. Okay.
N plus 1.
Where did I put? Oh yeah, thank you.
Do you want us to memorize the Taylor series, like the equation or the?
Well, I've kept giving it to you, so I pretty much have to keep doing that. But it's, it's not something you have to have memorized going forward forever, so it's okay. But can somebody just tell me what it is right now?
F to the nth derivative of A over N factorial times x minus A to the n.
Kick ass. So of course here, the first term is 0, right? So this would actually be 1 to infinity. Fn evaluated at A is this business. I really want you to be cool with what's happening. I just replaced this with what it is. Now here's where something interesting happens. You guys see anything you can do there? Any simplification you can do? Of course, I should have put a 1 there, but things happen.
You can cancel out the factorials.
Yeah. This one you could
Yeah.
break out, right?
Yeah, it just becomes n times n.
Yeah, n times n minus 1 factorial. These cancel, so I get crazy sauce. And let's write some terms out. Let's just see what the natural log is. Now, to me, when I first learned this stuff, it just was freaking amazing to me that just this basic idea, give me a function, I can make this infinite polynomial. Do you care if your answer is exact? If not, just go out a few places in the polynomial. I'm like, oh my God, that's so freaking cool. So when n is 1, what do I get here? Then 1 squared, x minus 1 to the first over 1, right? Wait a minute. Yeah, okay. So I get x minus 1. Cool.
Yeah.
Plus, minus, right? When n is 2, I'll get x minus 1 squared over 2, plus, when n is 3, I'll get x minus 1 cubed. Mucha. Over 3. Blah, blah, blah. So if I want to know what the natural log of, what's a good thing to try to put in here to test this? Yeah, real quick. That is not a, no,
That does work.
you're kind of joking, but this is a really good way to make sure. The answer better be frickin' 0, because we know the natural log of 1 is 0. And when I put a 1 in, what do I get? 0, 0, 0 forever. So it's 0. It's a beautiful check. Make sure it actually works for the thing you built it around. If it doesn't work for the thing you built it around, okay. Somebody give me one that's different from 1 that might be good to try.
2.
Huh? 1.5, sure, okay. 1.5 is relatively far away from 1, so if we only use 3 terms, we might not get a great approximation, but let's see how close we get. So this is approximately 0.5 minus 0.5 squared, which is 1/4 over 2 is 1/8, which is 0.125, plus 0.5 cubed, which is what is it, Jeff? 0.125 divided by 3, which is stuff, 0.04, somebody help me out. 0.04, 16 forever, okay. So what is that? Let's see. Check. So let's see, it's 375, so it's 41666? If I did that right, yeah? So what is the natural log of 1.5?
0.405.
Yeah, considering that that's relatively far from 1, that's pretty damn close, yeah. We only did the first three non-zero. Technically, it's the first 4 terms. You guys with me? Because the first term is 0. But it's the first 3 non-zero. Yeah. And we got pretty damn close just doing that. Now, if we try to do 2, it's going to be much further off. It's going to be relatively decent, but okay, maybe. Okay. And again, don't forget, it feels like it's just us giving you more work to do, but integrating things like x squared, e to the negative x squared, which is impossible to do by hand. It's impossible to do this. And then you throw a series in there, and you can approximate it as close as you want. That's some seriously cool shit. I mean, that's immediate power of this. Okay. In fact, I mean, I can't remember if I told this class this, but if any of you guys do any computer programming, I might have said this. Very often what happens if you're trying to create a computer program, there's a point where you need an integration subroutine. It's integration subroutine. And there's these little packaged different integration subroutines that have different expectations and different limits and different whatever. So depending on what you need, you can pick one to kind of fit into your program, right? Now, if you don't do any computer programming, everything I just said is like, but some computer subroutines actually are built on the idea of knowing the summation and going to a certain point depending on what you ask for, right? It's kind of silly. Not all of them. Some of them are, but definitely not all of them. There's better ways to do it in general, but still, that's one place you can see them in action.
Are there any other places you can see them in action besides computer programming?
Well, yeah, I mean, it's so in a lot of physics. Physics is built off of integration because we observe flow rates, for example, and then we want to know something about the total amount, which is always going to involve an interval. So very often our observations are changes in things. And then we want to know the actual state of things, which is an interval. And then depending on our observations, the function we're actually wanting to look at could be any damn thing, right? And very often in physics, we just want a decent approximation. So yeah, holy shit. Now, every field you would go into that utilizes these, there are modifications. There are, what's the name I'm thinking of? There's adjusted methods where they make assumptions and they kind of truncate the work and so forth, right? Yeah. Sort of like the calculator, when you ask it to find roots, it uses Newton's method. Remember Newton's method from Calc 1? Anybody remember Newton's method? Where you go sit under a tree and wait for something to hit your head. No, it's the one where you did, no, I'm not going to do it, okay. But the calculator uses a modified version of Newton's method to correct for certain instances where the answer would actually be undefined because of the way that the method works itself. So you just adjust the method for your specific needs. So every field takes a theoretical thing like this and just adjusts it to meet what they need, right? Anyway, that's a little too much. So I'm really curious if you guys go further in whatever fields you go into. So if you go into engineering, they will use a modified version of this at some point. If you go into aerospace, if you go into pure math, of course, you're going to see this. If you go into physics, yeah.
So is pure math just the, like...
Yeah, pure math is the unadjusted, theoretical, perfect, right? And it's perfect because it's not bragging to say we get it perfectly, because in order to do that, we have to go to infinity. So like another field is like, right, we'll wait for you to go to infinity, right? We're gonna frickin' do as much as we need. So they adjust it knowing they're gonna wanna chop it. There are adjustments you can make to make the result closer because you know where you're gonna chop it. So, anyway, all right. So it depends on what field you go into, how they're gonna modify that. And of course, a lot of fields have just software subroutines that do it for you. So, but we're the humans. We have to know what the hell it's doing. Okay, sorry. That was all a side note. Any other specific questions? One last thing about physics, they use something called perturbation theory, which is we assume a perfect thing and then we start perturbing it with, like for example, we assume a frictionless surface, then we go, oh, there's friction, so we solve the frictionless surface, and then we introduce something, we modify, and then we introduce a new, oh, there's also air resistance, oh shit, and then it's sort of equivalent to the further and further terms of this. It actually ends up looking very, very similar to this. Yeah, sorry. Which, number 7? 7? Okay. So how do I do the slope of a, wait, what was this, where to go? Oh, 7 is the one. 7 is the one that would be extra credit. But just to remind you, so remember, so dy dx, and y is r sine theta, right? X is r cosine theta. Therefore, dy would be dr d theta sine theta plus r cosine theta. This is product, right? Hey, I'm not going to do all this, but you see how you can do the same with for dx? So this will end up being this big ass, this on the top, and then something very similar on the bottom. So what would you put in place of r would be the function I give you. So you put 4 sine 3 theta there, take its derivative, times sine theta plus it, times cosine theta, right? And then at the end you would plug in pi over 3. So I did it on the key, but this is the one, number 7. That is from the calculus for polar coordinates section. Something that only one person brought up to me, WebAssign, for some reason, when I ported it over to the new edition of the book, it put some 10.4 problems into the 10.3 homework. So if you noticed that and didn't say anything to me, all right. Shit, I could have just done all kinds of weird things to you. And you're like, all right, I guess I'll do this. Like, so that's not your fault. And I don't care. No, I don't like on homework. But I have no idea why I did that. So when somebody showed it to me, I'm like, oh God, this is another example of this freaky ass online homework bullshit. But I'm glad it helped some of you guys out. I really am. I don't want you to, whatever works. Okay, so I'm sorry about that. So some of you guys got more practice with this than I intended, which is great, because now you'll be ready for the bonus question. And just in case you want to know, dx would be dr d theta cosine theta minus r sine theta. So what would this look like? It would be derivative of this, put here, times sine theta, plus it, right, it, times cosine theta, and then something very similar on the bottom, right? And then you just plug a pi over 3 into all the thetas, because that's the theta that I'm interested in. That's the angle I'm interested in. Does that make sense? No? So I mean, just knowing this and this, you can create this, and then just plug shit in, right? On one level, it's really kind of cool. I have no idea if any of you guys feel the same way, that dy dx for parametric, for polar, is actually that straightforward. The result looks gross. That's because it's product rule. But it's pretty damn straightforward. I know what y and x are here. In parametric, they tell me what y and x are. So I just take the derivative with respect to t, and I get the derivative in general. Okay. So just to be really clear, I can't remember if I said something like this on Monday. Number 6B can totally be on the final, not a bonus question, because we did do section 10.2, which is where integration for parametric was. It's the calculus with polar stuff, like number 7, that was not, that was in that section 10.4 that we didn't do officially. Right? Okay. Let me ask you this here.
Zero,
Why?
because x to the n would be 1,
Good.
and 1's in the,
So if x was 1, I would get the sum of Cn. This converges at 1, correct? So if a series converges, the limit of what's inside of it must equal 0. Kick ass. This is a little bit like the question I asked you guys about negative 3, what can you say about f of 2, whatever. You remember that kind of question?
yeah.
Just want to put that up there because this is a good question to ask, but since I asked something like this already, that's not going to be the conceptual question on the final. Yes, I'm excited about conceptual questions, Jeff, yes. Give me many, many of those. Um, 8D, what's something to be careful about when you get to what you think is the answer?
Make sure it's in the right quadrant.
Yes. So you know that point that I gave you, negative 12, 5, what quadrant is that in? Second quadrant. When you do the inverse tangent, you're going to get something in the fourth quadrant, right? So if you do the arctangent and you get blah, 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 and you get negative 0.3, that's negative 0.3 radians. That is definitely in the fourth quadrant. You guys agree with me? Right? How many radians is this? How many radians is like this? You could do it. What is that? What's the reference angle there?
-5/4.
Pi over 2, right? And pi is about 3, correct? So this is roughly negative 1.5, and of course, to be more precise, 7. You with me? Yes? So negative 0.3 is definitely in the fourth quadrant. But let's say I need to be in the second quadrant. How do I change this so I get an angle that's in the second quadrant? Yeah, add pi. If you add pi to this, so it'll be pi minus 0.3. Right? So just, it's at the beginning of the problem, just go, okay, that's in this quadrant. My answer better be in that quadrant. What does arctangent give you? The answer to arctangent will always be angles that live where? Oh shit. What's the range of arctangent? And the way to remember this is, what's the domain of tangent have to be so that I actually can invert it? What is the center tangent? Because remember, there's an infinite number of them, right? So what's the center one from to? Where are those asymptotes? Yeah, negative pi over 2. Pi over 2. So if we just chop it off to only, so therefore the arctangent, which flips this, has an output of negative pi over 2 to pi over 2. That's why it gives you fourth quadrant shit and first quadrant shit. So if your point is in the second or third, you're going to have to adjust that. Whatever answer you get, you're going to have to adjust it. I know it's a small point. It's one little problem, but might as well kick that thing's ass, right? Okay, so you know that problem. I'm going to give you something in the second or third quadrant so that you do have to adjust it. You know I'm going to do that. Yes. Which, I'm sorry? 8C. So I did 8C a certain way on the key. If anyone tried 8C, or if you're looking at it right now, what would you do with that?
Change it to R.
Was x minus y equals x1?
Yeah.
Okay. Yeah, what would you do?
Just change it all to.
All right, so what goes here?
R cosine theta. R sine theta. R cosine theta times R sine theta.
And then isn't there some cleanup to do here? If you leave it like this, how many R's can you kill? Not all of them. You can kill one out of everybody, right? Divide everything by 1 R, yes? So it's be cosine minus sine equals R sine theta cosine.
Okay.
And I would be okay if you left it there, but just to point this out, divide everybody by x. What do you get? Divide everybody by x.
Negative y over. Oh yeah.
All right, now replace it. What's y over x?
Tangent.
What's y?
R sine theta.
Yeah, that looks a lot cleaner, right?
Yeah.
And of course, you would get there if you divide this by cosine. Do you see how that's tangent? And that's 1. If you divide by cosine, yeah? So don't forget, you are okay. It's okay to simplify the rectangular when I give you, right? But also, you don't have to. It just means you're going to have a little bit of cleanup when you do this. But make sure if something cancels, holy shit, do it. If there's like terms, put those together, right? Don't just do one thing and then stop.
When we finish our final equation, do you want like all signs on one side and all cosines on the other?
No, to be honest, I would totally accept this, but you should sort of solve for R if you can.
That's what I meant to say.
Oh, okay, sorry about that. And then here you just divide by sine, yeah. But if you stop here, stop there, there's really no more simplification. It's just solving for R, which is not amazing, but just make sure to cancel stuff that they'll cancel, put stuff together that go together, those kind of things. All right, let me give you guys the answer key so you get some time to look it over. Find all the mistakes I made. And I'm very sorry about this, but I basically remembered to do this morning, so it's a little bit, especially number 1B, a little bit jumbled. Now on 2A, I did direct comparison, but what else could you use for 2A? Limit comparison, yeah, that would work too. Limit comparison works beautifully on like either like roots with polynomial ratios. I mean, it just eats those up. Because if you, so on that problem, how do you do limit test? How do you know what the other sequences you want to make a ratio with for this? So an in this case is rad n over, what was it, n squared plus n? So what do you want bn to be? It's basically the sequence that that's trying to be. So if you sort of ignore this guy, what is that trying to be? 1 over 3 halves, so 11. So if you just do bn is 1 over n to the 3 halves, and you set the limit of the ratio of those two things, you'll get n to the 1 half over n squared plus n times n to the 3 halves, and you see how that fills it in? Isn't that nice? And then they're the same degree, so then that's 1, and that's between 0 and infinity, so therefore they do the same thing, and so like blah, blah, blah. Right? And you don't have to worry about the inequality going the right direction, all that kind of stuff. You with me? But I just did direct comparison, because to be honest, on this problem, direct comparison is much faster. And like I said, 1B got a little messy there. I was trying to cut corners, which always gets me in trouble. Let me see, I think most of it's legible, otherwise, at least, you know. Oh, in case you missed this, what I said earlier, I said this a couple times, so I think most of you guys heard. Number 3, I made a nifty power series without any regard to endpoints. So if you go to try to check the endpoints in number 3, you end up with a series that's like one step above where we got to, right? So for that problem, don't worry. The one I give you on the actual final, I will check it ahead of time so I know the endpoints are actually something we could do, right? So for that one, you don't have to worry about the endpoints.
What does it say 1B the answers?
Which one, sorry?
1B.
1.
4L and 3 plus 2 plus.
Oh, shit. You got cut off. I love it. What would that be? Oh, plus natural log of 5 over 2. Yeah. It's over there. It got kind of like shunted at the end. Do you see where it says before that, 4 natural log of 3 minus 1 plus 3? And then underneath it says plus natural log of 5. Yeah, there you go. That's what my work looks like when I'm trying to cut corners. Number 4, let me see. Was it 4? Yeah. That's the one where you had to create your series based on a known series, the e to the x. And then you had to integrate it. I kept figuring out that I had to go further and further, which is basically the way you should do it, right? You start with the first term, which is 1, and then you have to minus 1 over 6 and plus 1 over, and you have to go far enough so that the first 3 decimal places stop changing. So you can see where I kind of stopped, and then I did it, and I'm like, oh shit, I kind of couldn't have stopped, and then, oh shit, and so I had to keep going. I kind of liked that the last fraction was 1 over 3, 4, 5, 6, but.
And that's 0.683.
683, yeah. And remember, you know how to check the answer. You can build that into y equals in your calculator and then tell it to do the interval and actually get that. And again, there's a class called numerical methods where you learn the algorithms that the calculators use to do things like integrate. They're based on things we learned in this class, but anyway, that's a nice way to figure out what the number's supposed to be. I think it's 6827 something, blah, blah, blah. So 683 is pretty damn good. And you only take 1, 2, 3, 4, 5 terms. Why do you think it took 5 terms here? What was that built around? Is that a Taylor series or more specifically a Maclaurin series? Which one would you call it? And how would you know? For number 4. How do you know that's not, how do you know I can call that a Maclaurin series? Look at the x piece. Is it shifted at all? Nope. Center 0. So that's Maclaurin. What am I integrating from to? For number part B. 0 to 1. 1 is relatively far away from 0. Yeah? So it kind of makes sense I had to go out more than a few places in my series to actually get the right answer, because at 1 I'm pretty far away from where, so the actual answer is pretty far from my approximation, so I had to go out a few more places. Everything I just said you don't have to know to do the problem, but still. And again, you can see on 5, you could call it lazy or call it efficient with my time, but we did it last time, so it's on the video from last time. I'm pretty sure we finished it all the way out, if I remember correctly. 5A and B. And don't forget, like on 6B, any of these, you could plug 1 minus cosine t all squared in your calculator, tell it to integrate, and check and make sure, it's going to give you a decimal, so then you just, whatever answer you got, you just make it a decimal and see if they're close. You can check your work, nothing wrong with that. In case you didn't hear this earlier, 7 would be bonus. That's from that section 10.4. Yeah. How you guys feeling? Do you wish that the final was Monday instead of Wednesday? No? Sometimes I'll be like, yeah, man, because this stuff will slowly leak out my brain. But that's why when you study, you want to study a little bit now and then study a little bit on Tuesday maybe. So it's not out of your brain come Wednesday. And you guys, on the canvas is my office hours. I showed you guys last time, but on the canvas is my office hours for next week. This week it's the same, but next week they change a little bit. Monday, of course, is a holiday. If you have a tutor that you've been going to in the Math Study Center, most of their schedules didn't change too much. There are a few people that had to change theirs because of their own finals. So, yeah.
And that's the option on like the extra credit or go to the Math Study Center?
Yeah, I can pull up the program, I can see who's been going in for tutoring. So sometimes if somebody has, they did a lot of homework and they did all these corrections and they still are like at 89.6 or something, right? Which is officially B+. If I go and see that they've gone into the Math Study Center quite a bit, I can use that as a little fudge factor, make it an A-, right? So if you've been going to the Math Study Center, there's been kept track of that. And then I can see that that's sort of like an extra little effort grade. Now, for me to do it, you have to be really close to some next level, right? So if you're like at a 69.7, which is failing, right? Which is a D, which is not, but you've been going for tutoring and you did all the corrections and so forth, that might be enough to push you over to a passing. Yeah. Okay. So just like last time, if I have wrung all of the water out of the rock, that is the questions you might have. Hey.
Will we be able to see our final grade on Canvas?
Oh, I don't use Canvas for shit. I don't know if you've noticed that, but what I always do is on the day of the final, I'll say, if you want to email me, I'll tell you. But normally I have it graded by the next day, and I have it into WC Online, or self-service, I guess now, the next night, right? So yeah, but you can just email me, I'll tell you what your final grade came out to be. Yeah. I don't like Canvas's grading thing, makes mistakes. One of my colleagues, she said it assumed some things and everybody's grade was higher than it should have been. So she had to go and say, actually, you're not passing, I'm sorry. Actually, you're not getting it, screw that shit. If I want it to be my mistake. I don't want it to be the silly program's mistake. So I don't use Canvas for anything except document dump, right? Okay. Oh, by the way, I was about to say, if you're ready, you don't have to sit here and stare at me, right? It's fine. If you have other questions, feel free to ask. Please, your God, if you have any corrections you have not done yet, especially the tests, they're the heaviest weighted things. Get help with your corrections. Give them to me on the day of the final. Normally what I do is, if I grade your final and you're really close to something, then I look at your corrections and so forth, see if it's enough to push you over, right? Okay. If you already corrected everything, awesome. But, yeah.
Whiteboard's still optional. We just want to have, like, using a whiteboard during the
Oh, sure. Just be careful. It turned out okay for you, man. You had enough stuff on there, but you always have to show the work on your test. So, but I understand, like, Madison had a really good point. She does a lot of work, huh?
just saying, I just do all my homework on whiteboard.
Yeah, she's in the Math Study Center. We have these whiteboard tables. If you've never been in there, so you get a little marker, you can do work on the whiteboard table. So she's like, I think that since I've done a lot of my stuff, I need that whiteboard thing. And I'm like, that makes sense. Just make sure to transfer that to your paper. Yeah. So if you want to use a whiteboard, just let me know. If I suddenly have everybody want to use a whiteboard, I might have to line you along the side so you're not like communicating to everybody. Hey, look what I'm doing. I have to get you away from each other. But we'll see. We'll see if anybody wants to do that.
We can take our final with the Math Study Center.
Just sit in the middle of the room and just wait for somebody to ask a question. Oh, that's like the one I'm doing. Sure. All right, guys. I'll see you next week. I'll bring some treats on the day of the final for us to enjoy.
So what is an A, like worth GPA wise versus an A minus?
So an A is 4.0.
Okay.
And an A minus would be 3.67. So the plus minus is always 0.33 up or down.
Cool. So it's just a
Yeah.
third.
An A plus is still a 4.0. It just looks nice on your transcript.
Yeah, it will look nice,
But it doesn't actually translate to a 4.33.
I don't know what I would need to get that because I'm at I think I'm at like a 95. I'd probably have to like ace the final if I want to bump
You
it.
on that last grade sheet I had at the very bottom, it says add so much for an A minus and then add so much for an A.
For an A.
You could actually. Oh shit! Well, it'd be a little more involved.
Because I'm like
On the day of the
like,
final,
I'm pretty
I'll have
confident,
this.
but I'm
I'll
like-
have the spreadsheet up here,
Mhm.
and if you want to, before we start it, you can say, "Hey, what would I need for an A plus?" And
Okay.
I'll tell you.
Cool. All right, appreciate it, Professor.
No problem.
You have a good one.
You too.
Thank you.